Hey guys, today we're going to learn about motion on a ramp, which is covered in section 3.4 of your textbook. So we're talking about the way things move when they roll or slide up or down a ramp. And today we're going to ignore frictions. Okay, so the best way to start this is to look at the extreme cases. So imagine our slope, so-called slope, is 90 degrees. In other words, we're sliding this block frictionlessly down a vertical face. What would the acceleration be in that case? And we're assuming we're here on Earth, so hopefully it jumps right out at you. This is going to be g. The acceleration is going to be g, which is 9.8 meters per second squared straight down. The thing is basically in free fall if it's a vertical slope. Now, what about if the slope is 0 degrees and it's just sitting there on a level table? Again, there's no downhill in this case, so it's going to be not accelerating at all. In this case, if it's level, it's going to be 0. So our extreme cases are if it's a 0 degree slope, it's 0, and if it's a 90 degree slope, it's going to be g. And if it's a slope somewhere in between those, then it's going to accelerate at some rate more than 0, but less than 9.8. So if the slope was very shallow, just 1 degree, it would just very, 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 very slowly slide down the slope. The acceleration would be very slow. And then the steeper the slope gets, the greater that acceleration will be. So I'm going to cut to the chase here, and I'm just going to give you the equation. All right, and here it is. Its acceleration is g sine theta, where theta is this angle here, the angle of the slope, and g is 9.8. Now the plus or minus means that if the thing is moving downhill, it's going. If you consider downhill to be positive, then it's going to go faster and faster down the hill. If you consider up the slope to be positive, then it's going to be going slower and slower and slower because of g. So g is negative if upward is positive, is the positive direction, because gravity is going to slow the thing down. So the acceleration is going to be negative. You're going to be slowing down. And g is positive if downslope is positive, in which case gravity is going to be making the thing go faster. All right, so A equals g sine theta. So for example, if theta is 30 degrees, I'm just going to go to the slope here. We'll get to the, never mind the writing there. Let's see, let's get rid of that. That'll work. Okay, so we're going to say if the slope is 30 degrees, we're going to take the sine of 30, which comes out to be 0.5, and then we're going to multiply that by 9.8. And we get 4.9 meters per second squared as our acceleration. So so if theta is 30 degrees, then the acceleration is 4.9 meters per second squared, because the sine of 30 is 0.5. Okay, what I want you to do is figure out now what the acceleration will be if the slope is only 28 degrees, and then to figure out what the acceleration will be if the slope is 65 degrees. We'll do that now. The 28 degrees is pretty close to 30, so you should be getting a number pretty close to 4.9, which is what I just got for 30 degrees. And think about, should it be a little bit more than 30, or a little bit more than 4.9, or a little less than 4.9? Okay, so pause the video and do that math and come up with answers. Okay, I'm going to I'm going to reveal the answers here in 2, 1. Okay, so for 28 degrees, it comes out to be 4.6 meters per second squared, which is slightly lower acceleration than a slightly steeper slope at 30 degrees. That makes sense. Okay, if you didn't get that, then pause this again and refigure it so you can get it. And now for 65 degrees, the acceleration will be 8.9 meters per second squared. Right, so that's a pretty steep slope. It's not quite in free fall, but it's getting pretty close. 65 degrees is 8.9 meters per second squared. All right, now what I want to do is run a couple problems here, calculations where we actually apply this. All right, and we're going to have a 10-degree slope, and we're going to have a ball that starts rolling up the slope at 8 meters per second. So the initial speed of the ball at the bottom of the slope is 8 meters per second up the slope. And we're going to figure out a few things here. So first off, we want to know how far up the slope we go. And we're talking about the distance up the slope as like driving up a road on a hill. We're not talking about the vertical displacement. We're just talking about basically the length of this hypotenuse here. Okay. So the way we're going to do this is we're going to use the very handy equation VF squared is equal to V naught squared plus 2A delta X. Because we're not given time, so we should gravitate toward this equation that does not include time. So VF squared. VF squared is the final speed, and we know that when it gets to the top, as high up as it goes, it's going to be going 0. So that's going to be 0 squared meters per second, quantity squared, equals the initial speed, which is 8 meters per second squared, plus 2 times A times delta X. So that means we need to find A. Now to find A, we're going to use the equation that we just used. Acceleration is equal to G sine theta, which is equal to 9.8 times the sine of 10 degrees. Put that here, 10 degrees, take the sine of it, multiply that by 9.8 equals, so A is equal to 1.7 meters per second squared. And in this case, the gravity is slowing us down, so it's going to be a negative number. The acceleration is negative 1.7 meters per second squared. So I'm going to put that in here for A, 1.7. All right. Plus 2 times negative 1.7 times delta X. Let's do that. All right. Now we'll solve it here. So we get 8 squared is 64. We're going to move that to the other side. So we have negative 64 meters squared per second squared, because we have to square the units too, is equal to 2 times negative 1.7 times delta X. All right. So we'll resolve all this. Negative 64 divided by 2 equals, divided by 1.7, change sign, equals 18.8 meters equals delta X. That's the distance up the slope. So this turns out to be 18.8 meters. Yay. All right, now what if we want to know the vertical elevation gain? So we want to know how high this one is here, the elevation. Well, for this, we actually have a triangle now. So for the elevation, we can sketch a triangle. We know this is 10 degrees. We just figured out that this side is 18.8 meters, and we want to know this one. So we can use SOHCAHTOA. Sine of theta is opposite over hypotenuse. So the sine of 10 degrees is equal to the y displacement times divided by 18.8. Because the sine theta is the opposite over the hypotenuse. So we're going to do sine of 10 degrees times 18.8. We already have the same number in there, so I'm just going to use that. I'm going to say times the sine of 10 degrees. Comes out to be 3.2 meters. So this is 3.2 meters. That's that side. Okay. Now, what if we want to know how much time it takes for this thing to stop? So time was not given to us. We figured all this. We figured out the distance. But what if we want to know how much time it takes? So time for the ball to stop, and then after it stops, obviously it will start rolling back down again. But how much time does it take to stop? And for this one, we can use. There's a couple of ways we can do it. But one way is to use this equation here. The VF, the final speed, is equal to the initial speed plus the acceleration times the time. This is on your AP gouge, I believe. So our final speed on this is 0 meters per second. The initial speed is 8 meters per second. Acceleration, we already figured out, is negative 1.7. Negative 1.7 meters per second squared times the time. And when we figure all this out now, well, this will become self-evident. So we're going to have negative 8 meters per second is equal to negative 1.7 meters per second squared times t. So 8 change sign divided by 1.7. Let's move it where we can see it here. start that over here. 8 change sign divided by 1.7 change sign equals 4.7 seconds. 4.7 seconds is the time that it takes to stop. All right. Now, finally, oh yeah, there's another way to do this too. There's another way to find how long it takes to stop. We did figure out this distance, the 18.8 meters. So if we want to, we can also do d equals 1/2 at squared. This comes from the big ugly one, x final equals x naught plus v naught t plus 1/2 at squared. We can figure this out by imagining that it is rolling down. So it starts at a speed of 0 and rolls to the bottom. And if we do that, then the initial speed can be 0. The initial position will be 0, and it leaves us just with this term. You can also do it by rolling up the hill, but you wind up with t that shows up in a couple places. But this is probably the simplest way to do it. Anyway, d equals 1/2 at squared. It's the distance given an acceleration. Now we know the distance is 18.8 meters equals 1/2 times negative 1.7 meters per second squared. Again, that's the acceleration we calculated at the start, times t squared. So 18.8 times 2, that gets rid of that, equals, divided by, let's see, 1.7 change sign equals, all right. Let's see, well, yeah, okay, we got to change our signs around here, but because that's what happens when you take a shortcut. Anyway, take the square root of that, and you get 4.7 seconds. 4.7 seconds. All right. If I have time, I may come back to this one to do it in a slightly more rigorous way. But anyway, I want to show one more example here. Now, how about how fast the thing is going? How fast the ball is going after, say, 4 seconds? So what if we want to take a snapshot of it before it has stopped, but we know it's rolled for 4 seconds. It's still moving upward, but we want to know how fast it's going after 4 seconds, just to pick a number out of the sky. And for this one, we can do VF squared, VF is equal to V naught plus AT. We can use that one again. Okay, so we're going to use this equation here. VF equals V naught plus AT. This is the same equation that we used over here, but when we did it before, we knew the final speed and we knew the initial speed, and we were going to find the time. This time, we don't know the final speed, but we do know the time. So ignore this here. I started solving the previous problem before in an earlier take, so just ignore this. Anyway, so final speed, that's what we want to find, is equal to the initial speed, which is 8 meters per second, plus negative 1.7 meters per second squared. That's the acceleration that we figured out at the start, times 4 seconds. All right, so we can just resolve all this. So we're going to go 1.7 change sign times 4 is negative 6.8. We're going to, and that is the change in speed caused by the acceleration. That's the acceleration times the time. So basically this is saying that we are losing, move it over here, we're losing 6.8 meters per second because of this acceleration. Now we're going to subtract that from the 8, so plus 8, which means that the final speed is going to be 1.2 meters per second. Okay? That's the final speed. Now, all these examples here, these pop up in different ways in the homework that you have for tonight, and there's some other things too, but I'm trying to show you the technique of how you solve these things. They all involve, all the problems that you do for homework involve finding the acceleration using this equation that I introduced today.